Thanks to the organizers for giving me the opportunity to tell you today about our work on polarons in transition metal oxides. When I had to decide what to talk about in this conference, I chose a pretty broad title because we've been working on polarons in a number of different materials. As you heard in the previous talk, we've done work on titanium oxide, but today I decided to focus on complex oxides because it's kind of interesting, different type of physics. So here are the people who've actually done the work. They have all left my group now. A number of them are working in industry, and Anderson Giannotti is a professor at the University of Delaware. So complex oxides, just brief introduction. I'm mostly going to be talking about complex oxides in the perovskite structure, which is illustrated here in the simplest case. It's a cubic structure, 5 atoms in the formula unit. You have usually a transition metal impurity in the center here, can be titanium, octahedrally coordinated by oxygen vacancies, by oxygen atoms, and then you have other transition metal impurities or potentially rare earth elements on the corners of the cube. And of course, these complex oxides have a large number of applications: dielectrics, magnetism, ferroelectricity, and they are used in a number of devices. The original motivation why we started working on these materials was provided by a very interesting finding about 15 years ago now, that at the interface between two of these oxides, in particular strontium titanate, lanthanum aluminate, both of these are regular band insulators, but you form an interface between the two, and at that interface, spontaneously, a two-dimensional electron gas develops with a very high density. And of course, this got people very interested in these materials, and there was a lot of debate about what is the origin of the two-dimensional electron gas, which I'm not going to get into, but when we started doing calculations in this system, we actually found that at an interface of this type, you can actually explain where the electrons come from. It's due to a polar discontinuity, and the density that you would expect based on the calculations is actually even higher than what is experimentally observed. 3 times 10 to the 14th per square centimeters. That's half an electron per unit cell. That's what you would expect for the ideal system. So then the question actually became not so much what is the origin of these electrons. The question became why in this particular system, strontium titanate, lanthanum aluminate, STO, LAO for short, why do you only get an order of magnitude lower carriers? And interestingly, by looking at different interfaces, still interfaces with strontium titanate, but with a different wider band gap material, it was found that you can actually find systems where this larger density is observed. Namely, if instead of lanthanum aluminate, you use gadolinium titanate, GTO for short, the group of Suzanne Stemmer did molecular beam epitaxy and demonstrated that you can actually get this full density of 3 times 10 to the 14th per square centimeter, half an electron per unit cell at the interface. And you can see in this TEM picture here that the interfaces are indeed very perfect. So that provided motivation for us to try and understand the physics of this system and particularly understand the physics of this gadolinium titanate. Now, it turns out that gadolinium titanate is a Mott insulator, and I'm sure most of you are familiar with this, but just to kind of put us all on the same page, a very naive picture of how I think about a Mott insulator. As I already said, strontium titanate is a relatively simple material. You can think of the valence band in all of these materials being made up of oxygen p states. The conduction band consists of titanium d states. And when you count charges, strontium has valence 2, titanium valence 4. That gives you 6 electrons from the cations, and you have 3 oxygen 2 minus to balance the charge. So a nice simple band insulator. Gadolinium titanate is a little different because if you think of the valences, strontium is 2+, gadolinium, it's a rare earth element, but for the purposes of what I'm talking about in this talk, the F electrons don't really play any role, and you can effectively think of the gadolinium as being trivalent. So one more electron is being supplied, and you would think naively, well, that electron will need to go into the conduction band. But actually, what happens is that you have this Mott metal to insulator transition where a band gap opens up, and you get a lower band of titanium d states, so-called lower Hubbard band, that is fully occupied and then separated by a band gap from the upper Hubbard band. So you can understand this in terms of the physics of the d states in cubic symmetry. They would, of course, split into T2G and EG states, but it turns out that in order to open up this band gap, you need to have a reduction of the symmetry. This happens by tilting and rotating of these octahedra in the material. You go to a lower symmetry structure that leads to additional splitting of these T2G states, and that allows you to split off this single D state that is going to contain that electron that forms the lower Hubbard band. And indeed, when we do first principles calculations, that is what we see. At the top is the band structure of strontium titanate, a simple band insulator. When we do the calculation, which I'll talk in more detail about in a minute, when we do that for gadolinium titanate, we see the oxygen 2p valence states, and then up here are where you expect the conduction band states to be, but they have indeed split into a lower Hubbard band, fully occupied, and an empty upper Hubbard band. Okay, so how do we do these calculations? Well, if you would use density functional theory with a traditional simple functional such as local density approximation or generalized gradient approximation, as we already heard during the meeting, you wouldn't get any of these effects. You wouldn't be able to describe them. You would just find a metallic system. So you need a better functional that actually allows for localization of charge, and we have found that hybrid functionals are pretty good for this. They are, of course, formed by combining GGA with a fraction of exact exchange, and that provides to some extent for a correction of the self interaction. You usually get much better band gaps in the material, and you actually are able to describe localization of electrons or holes much better than you would with the traditional functionals. So we specifically use the so-called HSE functional, Heitz, Kuzeria, and Enzerhof, as implemented in VASP. So again, we apply this to strontium titanate, simple case. When we do it for gadolinium titanate, in order to allow for these tilts and rotations of the octahedra, you need a larger unit cell, of course. It turns out that the 20-atom orthorhombic cell is actually the stable structure. That's what experimentally observed. And it's for this cell that we calculate the band structure that I already showed to you. Okay, so that's how we do the calculations. We understand the physics of this splitting in lower Hubbard band and upper Hubbard band. So what is the value that we get for this splitting? So physically, splitting between the lower Hubbard band and the upper Hubbard band within the Hubbard model, of course, has to do with the Coulomb repulsion parameter U. When we do the first principles calculation, we can explicitly calculate what that gap between lower and upper Hubbard band is, and we find a value of 2 eV. Now, to be honest, I wasn't totally sure whether this value would be very accurate. As we already heard in hybrid functional approaches, they are not perfect. Well, there is this mixing parameter, which we set just to the default value of 0.25. In materials where the band gap is known, that mixing parameter is often adjusted, but here we didn't really know what the band gap is, so we just set it to the default value. This is what we get. So this was our prediction, and we were actually very fortunate that as part of the experimental project that we were engaged in, as I was saying, Suzanne Stemmer was growing very high quality material with molecular beam epitaxy, and Professor Debdip Jena at Cornell University was doing optical experiments, and he could actually do photoluminescence excitation as well as photoluminescence experiments to check the properties of the material, and he actually observed a very strong luminescence visible to the naked eye that was peaked at around 1.8 EV, okay? And it's very compelling to associate this with the gap in the material. So 1.8 EV is a little bit smaller than the 2 EV that we got out of the hybrid functional calculation, but overall we were pretty satisfied with this agreement, and we really felt that this value around 2 electron volt is the correct value for the gap in this material. Now, when we started talking about this and when we tried to publish this, we got a lot of pushback because there is a large community of people who are working on complex oxides, and yeah, actually, before I get to that, let me just make a brief comment about the brightness of the luminescence, because you may be thinking, as I was originally thinking, well, these are transitions between an upper Hubbard band and a lower Hubbard band, and both of these consist of D states, and aren't you going to get like a very small optical matrix element because just of the symmetry of the transitions? Actually, you get a very strong transition because, okay, the physics is that it's all related to D states, but there is actually extremely strong mixing with the oxygen states, okay? And so we can see that in a decomposition and in partial densities of states, and due to that mixture of oxygen, when we calculate the absorption coefficient, you actually see an absorption coefficient on the order of 10 to the 5th, which indeed means that it's going to be a very strong visible transition. Back to the issue of getting pushback from the community. Within that community of people who were traditionally working on this, it had become almost accepted that the band gap of gadolinium titanate, as well as similar rare earth transition metal oxides, would be on the order of between half an EV and 1 EV. And that had been, quote unquote, established based on optical conductivity measurements. Optical conductivity, it's a more complicated experiment, but ultimately my understanding is that it depends on the optical absorption, the absorption of a photon across a gap, and you can see the signal of that absorption, and the onset of the conductivity in gadolinium titanate was determined to be around 0.7 electron volts. And as I said, this is not just for gadolinium, but for a number of other rare earth transition metal oxides. it had actually been observed to occur at similar energies. Okay. So a lot of people simply didn't believe that the band gap could be 2 eV because everybody thought the band gap was much smaller than that. So that put the burden on us to try and explain these previous experiments. Now, of course, when you do this sort of absorption experiment, the data is absolutely what it is, but all you really know is that there is some kind of excitation process going on, that a photon is getting absorbed by the material, and that leads to an optical absorption. But to me, that doesn't mean that it has to be across the gap. Okay? So we started to think about other types of excitations that might explain these results. And well, we're more than 10 minutes into the talk, and you may be thinking, well, is he ever going to talk about polarons? This is where the polarons come in. Okay, so we had been doing work on polarons. My student Joel Varley did a rather comprehensive study of various binary oxides back in 2012, and found hole localization in most of these materials. And then in parallel, we had been looking at self-trapping of electrons in work that you already heard referred to in titanium oxide, rutile. You see trapping of electrons, and that led to very nice collaboration with Ulrike Diebold for studying these polarons at surfaces. So we were aware that in all of these oxides, polarons can play an important role. And in fact, in materials like gadolinium titanate, there had already been discussion of polarons. One person who's done a tremendous amount of work on these materials is John Goodenough, who recently got the Nobel Prize. And he had published papers on electrical transport in these materials, in which he had discussed the transport in terms of the presence of polarons, specifically small hole polarons, okay? When I'm talking about hole polarons in this Mott insulator, I'm not talking about polarons associated with oxygen states. Because if you remember the band structure, yeah, the oxygen states are still there, but the equivalent of the valence band in this Mott insulator is now the lower Hubbard band, okay, which consists of occupied d states. So when I'm talking about holes, I'm talking about missing electrons in that lower Hubbard band, okay? And that comes about because these materials, as you grow them, either due to defects or unintentional impurities, tend to be unintentionally p-type. That would lead to the presence of holes, but these holes localize and you form small polarons. So the presence of polarons in this material was already accepted, and we started thinking about whether these polarons might actually be playing a role in these optical experiments. So we wanted to do a first principles calculation, and from Aaron Deskins and other people, you've heard about how one does these calculations. Set up a large supercell, you introduce a hole, and if you don't introduce any distortions in the material, you're going to find the hole to be delocalized, but then when you introduce some kind of perturbation of the atomic positions, you find easily that the hole wants to localize on a titanium atom. Okay, so what does that mean in this case? As I told you in gadolinium titanate, the titanium atoms actually want to be titanium 3+ because they have this localized electron on them. So introducing a hole effectively means that out of all of these titanium 3+ atoms, one of them becomes titanium 4+. Okay. That's the whole localization. So we can do the calculation of a structure, and we can do the calculation of the energetics. So we can compare the energy of the self-trapped hole of the polaron with that of the delocalized hole. The energy difference between those two equilibrium structures we call the self-trapping energy. But then we can actually get more information out of the calculation that we do by analyzing this so-called configuration coordinate diagram, which is a way of presenting results that we and other people have often used in the context of describing point defects, but it works equally well for describing the physics of polarons. So the small polaron is the lowest energy structure. If you make distortions of atoms around the equilibrium structure, you get a roughly parabolic shape of the energy as a function of the distortions, okay? We summarize these distortions in some kind of generalized coordinate. If it would be just a breathing relaxation of surrounding oxygen atoms, basically this generalized coordinate can be just the distance between the titanium and the oxygen, but you can also describe more complicated distortions within this one-dimensional model. So this red curve then describes the small hole polaron. The blue curve is a curve that we can generate for the delocalized hole, okay? And the energy difference between the minima of these two curves is exactly the self-trapping energy, which we calculated to be 0.55 eV. It's quite large, but within this picture, we can actually get more information out. For instance, how much energy does it take to do an excitation from the small polaron state to the delocalized hole state, okay? And in this diagram, if I draw a vertical arrow like this, it essentially corresponds to absorption of a photon, right? On the time scale of the absorption of a photon, kind of in a hand-waving way, you can say, well, the atoms can't move. You fix that generalized coordinate, and you're going to need a photon with an energy of 1.1 eV to actually make the transition from the localized to the delocalized state. The real situation is a little bit more complicated, and I'll need to talk about that. So I described one type of excitation that you can think about where you would go from a localized hole polaron on a specific site to a delocalized hole. Another type of excitation that you could think about is where you move the polaron. You move it from one titanium site to a neighboring titanium site. So we wanted to consider both of these scenarios to be able to study excitations. Okay, and for the process of essentially moving the polaron from site A to site B, you can draw similar configuration coordinate diagrams. So in this case, of course, the energies on the two sides are the same, but you can see, well, in order to move the polaron, you actually need to move it over the barrier. This measured barrier is actually, well, this calculated barrier is actually in quite good agreement with measured barriers based on transport measurements in this material. But again, you can see that instead of a thermal excitation to go over this barrier, you could, in principle, use absorption of a photon to go from the red curve to the blue curve. Okay, so these vertical arrows in these diagrams that I showed you, I said they correspond to absorption of a photon, but that's a little bit simplistic. This energy actually corresponds to usually what you would see as a peak in an absorption spectrum. But most line shapes of optical absorption are not sharp peaks, they are broadened. Why are they broadened? Because you have lattice vibrations, okay? And we can actually easily put that into the description in the context of these configuration coordinate diagrams where as I said, the curves are roughly parabolic. Think of a harmonic oscillator. You have vibrational states. So for the ground state here, I've just schematically indicated the ground state wave function of a harmonic oscillator. And at modest temperatures, you're actually usually only going to be in the ground state for the, of the vibrational system for the ground state of the electronic system. But when you excite up to, for instance, the delocalized state, you can actually not only excite to the ground state, you can also excite to excited vibrational states of that upper curve, and that means that your transition is going to be broadened, okay? And we can take that into account when we effectively calculate an optical absorption curve, and these are the results of that, and actually for both of the cases that we looked at, going from a small polaron to a delocalized hole, or going from a polaron on one side to a neighboring side, the results are actually very, very similar. As I already said, the peak of the absorption occurs around 1.1 EV, and the onset actually will occur at what is often referred to as the zero phonon line, just the energy difference between the minima in the two curves, which in our case corresponds to the self-trapping energy. So that's at about 0.6 EV. So what you would actually expect is that optical absorption of a photon by a small polaron in these materials will occur with an onset of about 0.6 EV, and then gradually rise to a peak of about 1.1 EV. So that's kind of roughly in agreement with these optical conductivity measurements that I already showed you. But again, we were lucky to be working closely with experimentalists who could do more detailed experiments in practice, meaning that they could do intentional doping of the material. Okay, so as I already told you, the as-grown material tends to be naturally p-type, and if I have time, I may give you some comments about why that might be. So the blue curve is kind of the not intentionally doped material, but you can intentionally introduce acceptors into the material by replacing a certain fraction of the gadolinium with strontium, going from valence 3 to valence 2. The strontium acts as acceptors. You get more absorption, a higher optical conductivity, and you can take a difference between these two curves, and that difference, in our opinion, then reflects the optical absorption that you get from these intentionally introduced holes which form small polarons. And you can see that the shape of that curve actually agrees remarkably well with the shapes of the curves that I showed you that we calculate based on these excitations. Okay, so we feel that these optical conductivity measurements that have been interpreted as giving you the gap in gadolinium titanate actually do not tell you what the gap is. They actually correspond to absorption of photons by small polarons. So in the few remaining minutes, I want to make some additional comments about what is the source of this p-type conductivity, and make some broader comments about point defects or impurities in such a Mott insulator. So we have done a lot of point defect calculations in a lot of materials, and you can use the same techniques for this material. Of course, it's again supercells. You introduce a point defect or an impurity, and you can calculate the formation energy of those point defects or impurities by comparing the energy of the system with the defect with the pristine system, and then there are additional terms that explain, for instance, what happened to in the case of an impurity that you introduce, where this impurity came from. It comes out of a reservoir, so that's why you have chemical potentials present. Also, if the defect or impurity is in a particular charge state, you have exchanged electrons with an electron chemical potential or the Fermi level, so you're going to see a dependence of the formation energy on the Fermi level. And so all of this is described in this review article that we published a few years ago. So for the purposes of what I want to talk about, I actually want to focus on this dependence on the Fermi level. And this is a typical diagram that we would analyze. You would plot the formation energy as a function of the Fermi level, which can range between like the highest occupied state and the lowest unoccupied state. And then for the defect in different charge states, you would get different lines with different slopes, and we usually focus on just looking at the lowest energy state for one particular Fermi level. And the kinks in those curves then tell us essentially about defect levels in the band gap, where you can make a transition from one charge state to a different charge state. So when we do that for defects in regular band insulators, this is the sort of result that we get. For instance, an oxygen vacancy in lanthanum aluminate, a wide band gap material. You can find the oxygen vacancy in a neutral or a +1 or a +2 charge state. And in this formation energy diagram, you would find three lines with different slopes, and the kinks indicate where you have transitions between these different charge states. So in gadolinium titanate, you essentially find the same physics, but with a twist, okay? Because these states that would correspond to the neutral or the positively charged vacancy in this normal oxide, as you can see, they occur within the band gap. But in the case of gadolinium titanate, that position within the band gap actually overlaps with the lower Hubbard band. Okay. So in the case of a neutral vacancy, the fact that you have a fully occupied state that overlaps with the lower Hubbard band is just fine, right? And so the neutral charge state of this defect will have its usual behavior. But in the case of the +1 charge state of the vacancy, what you want to do is take one electron, remove one electron from the system, and it would need to come out of a state located within this lower Hubbard band. And of course, you can't do that. You can't have an empty electronic state overlapping with a fully filled band in the material. So effectively what happens is that you're creating a hole in the lower Hubbard band, and as we already know, those holes localize. So the vacancy in the +1 charge state actually, you can draw it in this diagram, but it actually consists of a neutral vacancy with a small polaron in the vicinity. Or if you want to describe a 2+ charge state, you would need to remove both electrons from a state within the lower Hubbard band. And again, you can't do that. You still have essentially a neutral vacancy, but with two small hole polarons in the vicinity. Okay, so that's why in a diagram like this, I draw the lines for a +1 and a +2 charge state as dashed lines, because they're not really charge states of the oxygen vacancy itself. They correspond to a neutral vacancy with small polarons in the vicinity. Okay. So actually I described the picture for the oxygen vacancy, but the picture is very similar for any point defect that you can think of in this material. We've looked at titanium and gadolinium vacancies, we've looked at antisides, we've looked at interstitials, and systematically what you find is that each of these defects kind of has a natural charge state, the one that's drawn in a solid line. It's not always neutral. For an oxygen interstitial, it would be a 2- charge state. And then the other charge state that we expect to occur for point defects like that actually consists of the defect in its natural charge state, but with small hole polarons bound to it. So I actually think this is a general picture for point defects in these Mott insulators, And I'm not actually aware of systematic experimental studies on these materials in terms of point defects, but it would really be nice to apply some of the techniques that we heard about to the study of point defects in such complex oxides. Okay. And what I said about point defects actually also applies to impurities. This is just one example. Carbon impurity, the way these materials are grown, there is often carbon around. So you would actually expect it to be unintentionally incorporated. Carbon on an oxygen site is the lowest energy state that we found. And as you can see from this diagram, it's again the same picture. There is a natural 2- charge state and then small hole polarons bound to it. And this then brings me back to why we started studying this. Unintentionally incorporated impurities such as carbon might actually provide the explanation for the unintentional p-type conductivity that is observed in this material. You have some of these contaminants and they will act, in the case of carbon, as an acceptor and give you these small hole polarons. Okay. So in addition to carbon, we've done other impurities. We've also done the strontium that I mentioned before, and the picture is always the same. So at the end of my talk, I'll just remind you that our motivation was to try and understand the behavior of charges and defects and impurities in a Mott insulator such as gadolinium titanate. We found the gap between the lower Hubbard band and the upper Hubbard band was much larger than what people thought it was. We think that's consistent with luminescence experiments, but then we had to explain why the previously measured gaps were so much smaller. We explained that in terms of absorption by small polarons, and then in the last part of the talk, I told you how defects and impurities can actually induce these small hole polarons. Thank you very much.
Thank you for a beautiful talk and this nice story. Okay, questions. First here, then here, then here.
In your talk, you described briefly the process of migration of polaron from one site to the other. Could you comment about, for example, the mobility or the DC conductivity in this case? Are there measurements?
There are measurements, yes. I think this paper by Goodenough that I mentioned looked at the number of rare earth titanates, and they reported conductivity, and it was interpreted as hopping conductivity with barriers that are similar to what I described.
I'm not sure who was first, but there's many questions, so first.
Yeah, I also have two questions, but I will start with one. So, as you say that you don't see the 2+ state of vacancy in this material as a charge state, but as a vacancy with polarons, then in titania, do you also think in that way? Because then it's the opposite, that it's...
Yes.
But you also, so the neutral state in titania, you would consider it a 2+ plus polarons.
So in titania, yeah, it's the opposite case where indeed the 2+ is then the natural state, because in titania you have a naturally n-type material, and the +1 and neutral charge states of an oxygen vacancy would consist of small electron polarons bound to the natural 2+ charge state. And I think that's what Elio described also in the experiments.
Can I ask the second one? So I also wanted to ask, do you expect any excitonic effects in this gadolinium titanate?
I don't think there has been any systematic study of this, neither theoretical or experimental. I mean, it's tempting to assign the slightly smaller optical transition energy seen in experiment then compared to theory, it's tempting to ascribe it to excitons. We have not done a systematic study. It's possible.
Okay, thank you.
Yes, thank you. What would be the nature of the first ionization state, which you could produce in a photoemission experiment, for instance?
The first ionization state of what?
Of pristine gadolinium titanate. So what would that be? I mean, just you create
okay, so you're saying you have the pristine material,
yes,
no polarons, which I think is very difficult to achieve. Well, in that case, I think it's just an excitation across the gap, right? And that
no, not across the gap, just remove completely one electron.
I don't see how you do that in an experiment.
With photoemission.
Oh, okay, you move it to the
Just
vacuum lab.
to infinity.
Well, I mean, that's just essentially a work function measurement in that case, right? So you would, I think you would find the position of the lower Hubbard band. And actually,
but would you expect this hole to form immediately a polaron?
Well, but you wouldn't see the hole, right? You see the signature, you see the energy of the state where the electron was removed. And actually, such photoemission experiments have been done at I think the Berkeley synchrotron, and they actually saw a signature of the lower Hubbard band in exactly the position where we expect to find it. Yeah.
Thank you. Thanks for the talk and the insights. When you compute the optical conductivity or the absorption, do you see phonon replicas, or do the experimentalists see phonon replicas?
The experiment, well, I showed you the experimental results. There is not enough resolution there to be able to talk about that. Where was it? I skipped over it. Yeah. So you can see the resolution is not good enough. In terms of the calculated results, I'm going to be honest with you, we did not explicitly use the full phonon spectrum in this case. We can do that. We do have the formalism where we would calculate actually the vibrational modes of the local structure and also take bulk modes into account and calculate the optical absorption line shape based on that full information. In this case, we didn't do that. We did a shortcut where we assumed kind of one dominant frequency and just worked with that one mode. So I can't really answer your question because we didn't do it in enough detail. And it's kind of a circular argument. We didn't do it in that much detail because the experiment didn't have enough resolution to do a meaningful comparison anyway. But if somebody wants to do the experiment, we're willing to put more effort into the theory.
Okay, so what you call this splitting of the lower Hubbard band, in some transition metal complex, you would call it a Jahn-Teller splitting. Would you call that Jahn-Teller? Could that be considered Jahn-Teller?
I don't. Well, ultimately, I mean.
Or is that the same physics, or
you can
same
call
physics.
lots of things Jahn-Teller when you get a lowering of the electronic energy due to a distortion.
Is a 3D1 TI 3D1
yes.
in a metal complex would make
yeah.
a Jahn-Teller?
Yes, yeah. and it needs to be accompanied by distortion, and that distortion costs energy, but ultimately the energy lowering due to the electronic structure gives you the energy gain.
Yeah, thanks, Chris. So I'm trying to reconcile these two pictures you project. One is this 2.2 volts band gap, but you show it on, I think, Consham diagram. And on the other hand, the Polaron picture, which you show on total energy diagram.
And you show that actually, okay, in Kohn-Sham diagram, you have 2.2 volts band gap, but then you say, okay, so I excite my polaron in my total energy diagram, and I have 1.1 volt. So first of all, what is the nature of state which is created as a result of excitation by 1.1 volt into this higher excited state? But B, I mean, if you would do, say, optical absorption spectrum, not simply Kohn-Sham diagram, for this material, would you get actually 2.2 volts band gap, or maybe it will be lower because of electron-hole interaction and everything else? I mean, so how reconcile to these two pictures? I mean, they are in different language.
Yes, I agree with you, and we should be more careful about this. Now, in terms of the band gap itself, I think actually maybe Stefan commented on this earlier, or maybe you commented on it. I mean, the whole point of doing the hybrid functional is that you are supposed to get a better approximation of the band gap, and in the case of an across the gap transition, looking at the Kohn-Sham states is equivalent to looking at the energies. You're not going to get anything different if you just remove an electron from the highest occupied state and you would calculate the energy of that. In the absence of polaron formation, etc., I mean, that would just give you the band gap. For the optical excitation energies, you're right, but I think the distinction that you're making is essentially included in our description in terms of these configuration coordinate diagrams, where the 0.55 eV is the level that you would see in the band gap based on an energy picture, okay? The 1.1 eV is actually closer to what you get based on the Kohn-Sham picture because that would not include relaxation processes. That would basically, I think this is extremely close to what you get as the difference in the Kohn-Sham states for the localized hole and for the top of the filled band.
Yeah, but I mean, I'm trying to see what is the nature of this conductivity, because you were all telling all the time that, okay, so there are photoconductivity measurements. So photoconductivity measurements mean that you excite things and then things become mobile, right? So in this story, say, what is the nature of mobility? So you excite, the system de-excites and then hops in a ground state, or you excite and the system becomes delocalized and say your polaron becomes delocalized and then conductivity is as a result of ionization of this.
Yes.
Or, so what is a mechanism?
Well, I mean,
if it is a second mechanism, it should be equal to the band gap. In that case, you would have 1.1 volt, because you need to have a delocalized state in which your hole will be moving. And that state will be the bottom of the conduction band.
Okay, so you mentioned two cases, and I thought you were talking about the two cases that I described here. There are two possibilities for the excitation. You either go to a delocalized state, and if that delocalized state lives for a long enough time, you're going to get conductivity out of that. The alternative
but where is that state with respect to the band?
That is a hole in the lower Hubbard band. And I mean, we started having this discussion as early as Monday morning. What is the time on which a polaron forms, right? And I haven't heard an answer to this yet, and I'm not going to speculate. But I think in the case of electrons and titanium dioxide, we think there is experimental evidence that the localization is not immediate, okay? In the case of titanium dioxide, you can actually think of a dual picture for the electron. It can be either delocalized or localized. So we think it is possible that delocalized states live for a long enough time to contribute to conductivity. Even if that doesn't happen, there is the second possibility, which is where with the aid of a photon, you enable the polaron to hop from one side to another side, and that also gives you conductivity.
So There's 2 more questions, one here and then we should go to the coffee break.
I have a question about the line shape of the optical absorption measurement. So at some point you showed a diagram, yeah, that one, where you have this Gaussian line shape.
Yeah.
So I guess my question is, the optical transition matrix elements from a localized state to a delocalized state should be pretty small. So did you try to calculate the strength of so it should be infinitesimally small, basically. That's what I'm trying to say.
In this case, we did not specifically look at the strength. It's not immediately clear to me why that would be small, because, I mean, for different materials, people have talked about infrared absorption, I think, right? I'm looking around the room. Maybe somebody can remind me who talked about that, but I mean, you get an IR absorption that is easily measurable, right? So, I mean, it's for a different system, but I don't see why it wouldn't be sizable in this case.
Well, I guess the reasoning, I mean, I don't know, I don't know the answer, but I'm just saying, so the reasoning would be that you are overlapping an object which is an atom, you know, wide with something which is kind of extended over a very large kind of area. So the overlap is very, very small.
Well, yeah, but you could make the same argument for optical transitions related to point defects or impurities. I mean, all of this formalism actually maps directly onto that other problem. And we're just finalizing a paper on the strength of radiative transitions associated with point defects, and that is quantitative. We do calculate intensities, and you get strong signals. So yeah, I mean, I see your point. I mean, maybe one thing that can somewhat reassure you is that I mean, the delocalized state is not a delocalized electron or hole over an infinitely large crystal, right? In practice, you actually have a wave packet describing the delocalized state. And because we're doing all of this in a supercell, we actually have like a poor man's description of such a wave packet. And you get a sizable matrix element. But that actually, I mean, it's not really an artifact of the supercell. It's, in my opinion, a realistic physical description of the fact that the delocalized state of the carrier will somehow be in the vicinity of your point defect or your small polaron, and that gives you a sizable transition. And this has been described in the context of point defects, and I think there's this notion of a Sommerfeld factor, which describes how localized the state is, and yeah, and that's taken into account.
A technical question, just very related to the supercell. How large a supercell you need in this case to have those localized holes?
Well, these are small polarons, right? So they're really, I mean, this is a pretty realistic picture. I mean, I should specify, of course, what the scale of the isosurface is, but it's like we usually pick 10% of the maximum density. But this is really sitting on one atom. So this is not a case where you need 10,000 atoms to describe a large polaron. This is really a small polaron, and I think in practice, it was on one of my slides, right? So it's 160 atoms.